In this video, I want to show you some simple binary ninja scripting techniques for us to easily carve out a secondary payload from a binary sample. Now, the story and the sample for this video actually comes back from a recent incident that the Huntress SOC was investigating. On the host, we saw an interesting file called login.dll. Now, if you wanted to triage this, just investigate a little bit, well, the first thing we could do is pretty simple. Just take a look at the properties. This is presumably a DLL file. Taking a look at the details here, apparently it's supposed to be, or at least allegedly, an NVIDIA Shadowplay Remux, NVIDIA GeForce Experience, and maybe just a driver, some specific file for some graphics card some way, somehow, with the original file name being nvspapi.dll. But is it really? One thing that we might notice is that it is pretty big. I don't know, depending on how you perceive the size of files, but 2.12 megabytes is something that we could be a little bit interested in. If you wanted to, before opening up Binary Ninja or anything else for debugging, maybe taking a look at the assembly, disassembling, right? If we were to open up login.dll, just kind of curious what the heck this thing might be, well, take a look at all of the sections in the text editor here, or even just the template when we're using the exe or the portable executable template in the 010 editor. Scrolling down at the usual sections, there is just some stuff here, but an odd unnamed section kind of down at the bottom, section 10. So at the very end of the file, there are just all these hex 90s. A lot of NOP or no operation if this were to be considered an actual machine instruction or like an opcode in assembly. Actually, apparently, based off the size here, there are 80,000 hex 80,000 of them. So a whole lot of junk, and if we wanted to, before we open this up in Binary Ninja or our disassembler of choice, I like to run dbloat. And some of you that keep an eye on the channel might have known that dbloat is actually a tool from a good friend of ours, Squibbly-Doo, another incredible security researcher doing super sweet stuff. It's just a simple GUI and CLI tool for removing bloat from executables. So simple, I've just got it downloaded from the releases, and it's extremely easy to use. We can go ahead and actually drag in the file, process it, and see what it does. Okay, looks like it does actually shrink it, carved out those hex 90 bytes that we didn't care about. And we could have done that manually in the 010 editor, of course, but in case this had anything else, I did want to run that through just that tool. Now we have a login_patch DLL that we can open up in Binary Ninja and finally take a look at this thing. Let me open up our login_patched DLL. You can see I have been taking a look at this just a moment ago to make sure everything was working smoothly. But before even digging into the disassembly here, I do want to bring us to, as it kind of loads, you can see as it's identifying things over on the right-hand sidebar menu, or that view map there. We could actually click into view and go take a quick look at the triage summary, because this will give us some good insight, tell us a little bit about the file that we would just otherwise be doing for our own analysis with other utilities. Kind of neat to get the DLL characteristics compilers use, anything else, any information about the binary that would be helpful. You can even see all the libraries that it uses, imports and imported methods or functions that it would call from any of those DLLs, and especially since this is a DLL or a dynamic link library on its own, we could be curious, hey, what exported methods or functionality do you actually have? There is one called run DLL. We could take a look at that, but it brings us to... Wait a second, hold on. Before we go any further, please let me take a second to tell you about the sponsor of today's video. When you're writing code, security might not be the first thing on your mind, but it should be. Vulnerabilities can sneak in from all over your code, libraries, or containers, and if you don't catch them, they can turn into real problems later down the line. And that is where Sneak comes in. Sneak helps you catch those vulnerabilities early and fix them fast without slowing down your development. And it's not just for your everyday projects. Sneak is also a super powerful tool for capture the flag competition. Whether you're competing to win or just playing to learn, Sneak can help you quickly identify vulnerabilities, giving you an edge in securing your application and scoring points. Plus, it's completely free to try. Just use my link in the video description to get started. jh.live/sneak. Huge thanks to Sneak for sponsoring this video. There is one called Run DLL. We could take a look at that, but it brings us to sub 1800078FF with arg1 passed in as an argument, and this does something strange where it actually has arg1 used as a mathematical part of a sum here to add on to hex 1020, and then call that as if it were a function, right? The parentheses invoking that as code. But we don't exactly know what that arg1 was, especially if it were be called with run DLL some way, so how. So I'm a little bit confused by that, truth be told. If you've got a sweet explanation, please do let me know in the comments, and you might be able to help me make sense of all the other tricks that this thing does. Because if we actually go take a look back at the _start function, where Binary Ninja put us to start, like the entry point here, that actually has some stuff where you would expect, okay, probably the arguments based off of like a main function in C or a compiled language, that uses, okay, a vector or a list of all of the command line arguments as it was invoked and ran, and then the number of arguments. But arg1 is just kind of a number, presumably in this case, int 64. They're checking if it's not equal to 1 for invocation, I'm going to assume, as the count of arguments. It'll exit out, which means it would just need to be executing itself. Then we do something with a var _28 with a loop up to hex 72, presumably just setting more data there, but that does actually get passed into the sub 18000781 function, which we could double click into to explore more of. This actually brings us in the middle, or at least close to maybe more of the top of sub 18000787. That did take a lot of arguments. Maybe we could actually keep track of that because we can see it's doing stuff with arg4, arg1, all of the parameters there. So if I hit escape on my keyboard to go back, we could see this was passed with the I counter that we were working with. 0 for argument 2, the address 478, arg1 as the 4th argument, arg1 as the 5th argument. So it's including arg1 a lot, and we saw that earlier with the run DLL entry point just as well. So what are they doing with this thing? They have a conditional here to check if arg2 plus 1 is less than or equal to some value, in which case they do something again based off of hex 72, calling us back into this exact same function. The exact same sub is where we're going to end up going again and again and again. Again, I need your help here. Let me know. Help me understand. Is that for some compatibility, for architecture, for memory space size stuff? I'm not super duper concerned with that. I'm more interested in this segment down below because we start to do more interesting stuff with arg4, which we know as it was passed into this function is actually arg1. Arg1 being a number and the same thing that was kind of passed to the run DLL export. It's weird to me that they end up using a lot of stuff with arg4 plus some value. You see this down below with arg5, which again, remember, was arg1 in the start call, but then they add into arg5 again. So just as a thought, I don't know, again, presuming if it were to be considered a number and it's referencing all the things that could execute, is it from the binary itself? Is it like reaching into and using whatever, hey, add new capability, features, and functions to run via the start or the base of the binary? And if that's what we're thinking, well, what is arg4 in this case going to end up being if I try to copy that value and then hit G on my keyboard to go to it? We know it's likely going to start at hex 180000 because that's everything that we've seen from all of the addresses that we see in the disassembly. But if I actually add in that hex value that we've seen as if it were being added to it, making it the right size, it actually says and tells us that's virtual alloc x numa, which if we, go there, we can see it's actually using a lot of the stuff from presumably the function table. And that actually makes sense if this were a call to virtual alloc x numa, virtual alloc in this case to just reserve memory space. Normally you've got the permissions, I think page read write execute. I'm not positive exactly what that constant is, but you normally see hex 3000. That just stuck out in my mind to me. But anyway, it's reserving memory and then using a built-in mem copy to copy the destination being, the memory that was allocated set as rax2, and the source arg5 plus this thing again, right? Or at least a new address we could copy and paste and go to if we didn't want to have to hand jam and figure out the zeros and remove our 0x to get us back out of the hexadecimal representation. You could just try to add this relative to where you are, but that is relative to where you are. So you'll need to actually bring yourself all the way to the start of the binary if you're treating this as the base. So pressing the control home button will bring us all the way there. Then when I G relative to that address, it'll bring us to data, which is something I actually want to explore. And it looks like gobbledygook, nonsense, and just a bunch of gibberish. No plain text characters, but \x likely non-printable character data, but data nonetheless in this big buffer here. I'm going to assume this is encrypted data. I think that's fair to say, right? And this is defined with a character buffer with a given size, which if we actually go back, ooh, kind of interesting. Oh, they're all resource data entries. Neato. Going back to the code in our function call where we saw this all happen, they were actually then iterating with the for loop up to that hex 2CA8 boundary, where they took rax2, now where it has that encrypted data, we're going to assume, and actually XOR it. You can see the caret XOR operator with arg5 plus this address. So is this now the key if it's going to end up doing some modulus, presumably modulus operator up to hex 12? Let's take a look at what this is. If we were to go to that address relative to the start, PDB file name is apparently a symbol set, but, oh wow, an interesting string there. Rel, GF client, shadowplay, all the NVIDIA little scam pretense for the malware. But this string GMZLVPP19 is, this must be the key for the XOR. So a simple little cutesy XOR cipher to be able to carve what will be new data out of memory and actually ending up executing it, right? rax2, again called with what would be arg5. Anyway, that is enough talk of the background context. Now let's play with some Python. I can hit Control P on my keyboard to open up like the command palette. And if I start typing Python, it can open that up and actually tell me, oh, Control backtick is the symbol or the hotkey to be able to get that console and Python displayed. And you might have noticed that terminal in the bottom left is just how you could click into it on the menu interface. But let me tell you, in this, within Binary Ninja, when you get to play with Python, you can actually access the whole dump that you're seeing kind of in the code here and the assembly instructions whenever you need them with a really neat BV object and variable here. BV is a binary view based off of everything that we've been able to read in for our binary, noting the start value. If I move my face out of the way, there's the base address that we saw previously. So if we were to do bv.start, make sure that is hex, we can extract that as a value for us to be able to work with and potentially pull out and do just this operation to XOR the encrypted data. So that means that this value, bv.start, is the base, and we can just call it that for sake of convenience, right? And we know that the value of the key that we end up using for this XOR operation is at the base plus this value, right? If I actually take base plus that value, and if we take a look at that in hex, we should be able to see just a location we can double click on to get back to the key, which means we can store that as a variable for us to work with. Not as the hex string representation, but as the real integer value. We also know the key length in that case, so we can just denote, okay, key underscore len should be that hex 12 that we saw both in the loop and in the actual length of that buffer. Then if we go back, we know the encrypted data is way up here, arg4 plus this value. That should be base plus this. Make sure that is displayed in hex for me so I can click on it, double check. Oh, no, that's the function call. Good thing we did that and got to test. Buffer is going to be the mem copy location, right? So let's use this one, base plus that value in hex. Pretty please. There we go. Now we have the encrypted data and we can see that actual hex2CA8. So that means if we want to extract the whole buffer, right, we need to end up making really just the start of the encryption data being base plus that. The length that we know would be this, copy pasting that. And then we could try to read with the binary view object. This is kind of neat, bv.read, where we're saying, okay, actually start at the encrypted data start position up to the length. Now, you can do this and you'll extract all this data out. We can just call that enc underscore data. And I'm sure some folks might be saying, or at least I saw and thought was neat, you could just do get data at var and pass in like the literal string here for the data value. Oh, forgive me. I think that's get data var at, which means it will not take the string, but the actual value. So base plus that hex ending there, of course in hex. Now we have that character data represented. This is the same thing that we just manually carved out above, but let me add the disclaimer, if Binary Ninja did not happen to get like the typing correct or bounds or limits, or if it just didn't figure it out smartly and maybe something were amok, then you might be shooting yourself in the foot. So if you can have enough sense and be tracking down beginning, end, buffer length, buffer size, try to use that as your own bounds, or at least what you could do. Anyway, we have our encrypted data, we have our key, we know the length of all of these things, at least we have the start value of the key. We'll need to do the XOR operation now and put it in to a decrypted buffer. So we can just use a list for that in Python. Empty array, empty list, the square braces, and I suppose we should really just get the key data on its own where we bv.read keylen. Now we have the key data, as expected. And now let's do our own XOR loop where we'll use two iterators I and j while we enumerate. So we have both the value itself and the index as we're iterating. Let's enumerate over all of the values, the actual data in the encrypted data, and then add into our new decrypted array as we're building this all out, actually taking the value that we know, j in this for loop, XOR'd with caret symbol for XOR, the key data actually indexed at, because remember the modulus operator to wrap around to the very start as we get to the end of 12 characters, hex 12 characters, I as our iterator, modulus key length, really. And with that, if I hit enter here and then a double enter, it should put it all together, and now I have decrypted filled out with a lot of zeros at the end there, but data. Like bytes, real bytes. So just to keep us cruising, what I want to do is actually save this as another file. I'm going to put it in the same directory as where we are. Let me just do a with open decrypted data.blob, write bytes as filp. Let's do filp.write decrypted. Oh, and I do want to make sure I put that in the same directory that I've been working in. Now when I hit enter on this, we actually need to consider that bytes. Haha. Wrap that in bytes, please. Dunzo. Can I now go take a look at that decrypted data.blob inside of the 010 hex editor, just to kind of get a feel for what it is. Maybe it could be anything. You could run file on it or trid or anything to try to identify it. But let me open up decrypted data blob, and then we get a lot of nonsense. So nothing particularly good. Oh, wait a second though. As we keep scrolling down, just taking a look, I see an MZ header and then the usual binary giveaway. This program cannot be ran in DOS mode. So there is a whole binary here, at least embedded eventually. Is there anything else? We could get to maybe the bottom. No, you can see all the strings for stuff it's going to continue to use. Let me just try to cut up from the start here, or maybe we could, I don't know if debloat would work from the top or not. But let's select all these bytes, delete them out. So we start with our MZ header, and then let's save this as a second stage.exe, right? Now, if I were to apply a template, I think I can tell it, hey, this is an exe. Yeah, okay, now it can make sense of all this. And do we have any strange data at the very end there? I don't think so. It's properly getting the end marker with some null bytes, whatever, but hey, debloat could run on this if we really wanted to. Now we might be able to fall down the rabbit hole and try to open up what would be second stage.exe. But I will admit, I did not intend on going through that for the video. Interesting though, it does have run DLL here and then a subroutine to, sleep WSA startup to what would be callback and connections. What do they have defined up here? Then they set value to data, which I'm not positive I know what it is yet. Then they do this over and over again based off of other data. But what does this subroutine actually do? Much more shenanigans. Now, this actually, I'm not gonna lie to you, becomes ginormous. The video is kind of already long enough, so we will press the easy button at this point, throw it into a dynamic analyzer, and I can kind of continue telling you the story. Let me just kind of go to the graph here, though. You can kind of take a look. This gets beefy. And then I'm not going to lie to you, for the actual rest of the investigation, there was a second DLL that was strange, and that was a ginormous file. At least in terms of code flow, here's a screenshot of how that graph looked and just all the functions kind of put into work here. This is me trying to zoom in so you can see it. Another analyst who is much smarter than me tried to dig into it for a bit, and I believe they said, hey, this actually looks like it is the Enigma protector, which I'm going to assume, I have not even looked at it, I'll be straight up, I didn't want to try. It's probably a pretty tough cookie if it's virtualizing a heck of a lot of stuff that it's going to do for the binary. But anyway, let's take the high road and do some quick and easy dynamic analysis thanks to the Cloud Sandbox. I'm a big fan of any run. Let me upload the file here. Considering this is a DLL, I am not positive if it's going to end up actually invoking it smart and right away. We might need to kick the tires with run DLL 32. I don't know if it'll be able to change the file extension and then do its thing, but we'll put it on the desktop and we'll use the interactive dynamic sandbox to be able to play with it here. Oh, no, okay, it's trying it with just the first export. Looks like it is seeing some action. Let me move my face out of the way. Oh, and this is interesting. It's tracking it down with what looks like System BC based off the network traffic and the Suricata logs. So if I take a look at that, just to kind of get a closer look, we can see the IP addresses that it's calling out to, System BC kind of being a rat, really command and control framework, remote access capability. I believe they use SOCKS in like a proxy way. And we can see connecting to that port, right? See the port description, all this stuff we could have probably seen in the WSA if we kept digging in Binary Ninja and spent the time figuring it out. But reverse engineering takes a long time and does not make for the best YouTube videos, right? Okay, looks like we're getting a little bit more info though. Oh, it should be over in the connections tab though, whenever we can see the communication to that server. Does it ever get anything back? Is that server still online? That's the only one, but it does send likely encrypted data. So not stuff we could readily get without a little bit more digging. But it does look like System BC, right? So if folks weren't familiar, there is a lot of info on it out and about. Looks like it was even used by the Black Suit Ransomware Gang, report from DFIR report. Other adversaries that use it. It's been around for a while. Looks like first samples go back to October of 2018, so now 7 years. There is a really cool write-up from Kroll, I'm bad at names. But I'll be sure to link this in the video description if you're interested to read a little bit more about it and see some other stuff that they do. But it's kind of neat in the proxy-based payloads and really what we did, what we got to put together given our binary ninja tricks, even if it's just carving out a binary from itself to mask some other operations, if it's even just as simple and stupid as an XOR cipher. We got to do some small stuff that I hope are maybe just some tricks you haven't done before and a way to more easily automate and streamline some reverse engineering effort. Hey, big thanks to my friend and teammate Alden Schmidt for helping me learn a little bit of Binary Ninja slowly but surely and some of the Binja scripting tricks. And if I may ask you just a humble favor, if you'd like to support all that we're up to, hey, take a look at Just Hacking Training. JustHacking.com. It is our new training venture for courses and lab activities, exercises, all this stuff to help you learn cybersecurity and more. Also, hey, maybe if you'd like more stuff even in your inbox, please do take a look at the newsletter that we're finally getting up and running. I'm pretty excited about it. jh.live/newsletter and other links in the video description. With that, please do give some love to our sponsor. Huge thanks to Sneak. And finally, thank you for watching this video. Please do all those YouTube algorithm things like, comment, subscribe, and I'll see you in the next video.